In this video, we are going to look at the examples for section 11.4. We're starting with this one. Use a tree diagram to construct a probability distribution for the number of twos in the 3 spins of the spinner. And you may recall the spinner looks like this. So we spin this 3 times and we want to know how many twos we're going to get. Well, we start this way. On the first spin, we get either a 1, 2, or 3. On the second spin, we get a 1, 2, or 3 each time. And then on each of the third spins, we get 1, 2, 3, 1, 2, 3. And I always hate the way my tree diagrams wind up looking. Even when I try to make them big. Okay, so here we have all the possibilities, and some of them aren't visible down there at the bottom. That up a little. That pretty much makes it all clear. And we can enumerate what each of these possibilities are. From up here, we have 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 3, 1, 1, 3, 2, 1, 3, 3. Now we've got 2, 1, 1, 2, 1, 2, 2, 1, 3, 2, 2, 1, 2, 2, 2, 2, 2, 3, 3, 2, 1, sorry, 2, 3, 1, 2, 3, 2, 2, 3, 3. And finally we come down here and we have 3, 1, 1, 3, 1, 2, 3, 1, 3, 3, 2, 1, 3, 2, 2, 3, 2, 3, 3, 3, 1, 3, 3, 2, 3, 3, 3. And we can look at this and we see we've got 1, 2, 3, 4, 5, 6, 7, 8, where there are no twos. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 with 1, 2. And we can count up the number of places where there are 2 twos. There are 2 twos here. That's 1, 2, 3, 4, 5, 6. And finally, we count the number of places where there are 3 twos. Well, there's only one of those. And I'm just going to do my math here quickly because there are 27. This is 21. This adds up to 28. So I made a mistake somewhere. That makes sense. 6. Yes, there should be 12 set numbers where there's only 1, 2 instead of instead of 13. That was my bad. So with this information, we can create a probability distribution. And the probability distribution is going to look like this. We can have our x, and that's our number of 2's, and our probability, p of x. So if x is 0, there are 27 ways to spin this, and 8 of them, the probability is 8 over 27. If there is 1, 2, probability of 1 is going to be 12 over 27, which we can simplify to 4 over 9. 6 2's, there's 6 sets of 2 2's, so that's going to be x is 2, probability of 2 is 6 over 27, or 2 over 9. And there's only one possibility for 3 2's. So that's 1 over 27. If we add this all up, we get 1. There is our probability distribution. Moving on. Find the probability of obtaining exactly 3 heads in 5 tosses of a fair coin. Okay, so we just want to know how many ways can we flip a coin 5 times and get exactly 2 heads? Well, the problem with this is that there are 32 ways to flip a coin 5 times. And obviously, you know, we can rule out anything where there are a bunch, where there's more than, we need to just figure out which ways can we choose 5. We just need to figure out what ways there are of flipping a coin and getting exactly 2 heads. Well, we can write out the possibilities. I can have head, head, tail, 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 or head, tail, head, tail, tail, head, tail, tail, head, tail, head, tail, 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 head. Or I can have tail, head, head, tail, 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 head, tail, head, tail, tail, head, tail, tail, head. Or tail, tail, head, head, tail, 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 head, tail, head, tail, 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 head, head. That should give us all possible ways of having 2 heads in 5 flips. And that's 10 possible ways out of a total of 32 possible ways of flipping 5 coins. So the probability of exactly 2 heads is 10 out of 32, or 5 out of 16. The probability of obtaining exactly 5 exactly 2 5s in 6 rolls of a fair die is a little more complicated, because now we're dealing with something that occurs where there are 6 possibilities every time we roll, right? Instead of, you know, we have an option of 2 things. Sorry, I'm just finding the information I need here. Okay, there it is, yes. Okay, so for this, we are going to use our formula. This is the formula for binomial probability. And that formula looks like this. You can find the actual formula, that's always good. Okay, here it is. The probability of X is equal to N, choose X, times P to the X times Q to the N minus X, which is equivalent to N factorial over X factorial times N minus X factorial times P to the X Q to the N minus X, where P is the probability of success and Q is the probability of failure. N is the number of repeated trials, and X is the number of successes. So we're looking for the probability of 2, and we've got N is, we were told that we're rolling a die 6 times, so that's 6 factorial over 2 factorial times 6 minus 2 is 4 factorial. And we multiply this by P to the, P is going to be 1/6, and we're going to raise that to the X power, X being 2, times Q is 1 minus 1/6, that's 5/6, to the 4th, to the N minus X. All right, so I simplify whatever I can. 6 factorial over 4 factorial is just 6 times 5 divided by 2, that's 15. 1/6 squared is going to be 1 over 36 times 5/6 to the 4th. That's a little more complicated. For 5/6 to the 4th, I grab my phone. There it is. 5 to the 4th is 625 over 6 to the 4th is 1,296. Okay, well then, I now have 15 times 625 divided by 36, and then divide the result by 1,296, which gives me 0.2009389. We're probably safe calling this 0.201. Just glancing at what the book actually gives for the answer there. Yeah, they give about 0.201, and that works just fine. So there is our probability for getting exactly 2 5s and 6 rolls. Here, a couple plans to have 5 children, and the probability that they will have more than, find the probability that they will have more than 3 girls. Assume boy and girl babies are equally likely. Well, to say that they're going to have more than 3 girls means that they're going to have 3 or 4 or 5 girls. So we need to find the probability of each of those events and then add them up. So what we're really looking for is the probability of 3 plus the probability of 4 plus the probability of 5. Okay, well then, I can start by taking the probability of 3. 3, that's going to be 5 factorial because we're looking at 5 events, over 3 factorial times 5 minus 3 factorial is 2 factorial, times the probability of a girl is 0.5 or 1/2. And we raise that to the x power, where x here is 3. And then the probability of a boy is still 1/2, and we raise that to the 5 minus 2 power, or 5 minus 3 power, which is 2. Plus 5 factorial, still 5 factorial, over 4 factorial times 1 factorial times 0.5 to the 4th times 0.5 to the 1st. Plus 5 factorial over 5 factorial times 0 factorial times 0.5 to the 5th times 0.5 to the 0. Okay. Well, one nice thing here is that each of these is exactly 0.5 to the 5th. And we can use that number. That's 0.03125. All right, so next, 5 factorial over 3 factorial is 5 times 4 divided by 2 is 5 times 2 is 10. 10 times 0.03125 plus 5 factorial over 4 factorial is 5 times 1 factorial divided by 1 factorial is still 5 times 0.03125 plus 5 factorial over 5 factorial is 1 times 0 factorial is still 1. So that's just 0.03125. So effectively what we have here is 16 times 0.03125, which is 0.5. Your probability, if you're going to have 5 children, the probability that there are more than 3 girls, Oh, I made a mistake here. I shouldn't have included this part because it says specifically more than 3 girls, not 3 girls or more. So we can get rid of that part, and this should only be 6 times 0.03125, which is instead 0.1875. There is our probability of having more than 3 girls in a family with 5 children. Next up, Gary Bell is a pitcher who is also an excellent hitter and has a well-established career batting average of .300. Suppose that he bats 10 times. Find the probability that he will get more than 2 hits in his 10 at-bats. Okay, so here n is 10. And, well, x is a little different because we're asking about getting more than 2. But that would mean we'd need to calculate this for 5, 6, 7, 8, 9, and 10. 3, 4, 5, 6, 7, 8, 9, and 10. So it's going to be easier if we let x equal 0, 1, or 2, and then subtract that from the total number of possibilities. Here p is 0.3 and q is thus 0.7. So we're going to take p of greater than 2 is equal to 1 minus the probability of less than or equal to 2. And we can do that with our binomial probability formula. We get 10 factorial over 0 factorial times 10 minus 0 factorial, which is just 10 factorial again, times 0.3 to the, that's to the 0, times 0.7 to the 10th, plus 10 factorial over 1 factorial times 9 factorial. I should note that this is 1 minus all of this stuff that I'm putting together here. Times 0.3 to the 1 times 0.7 to the 9 plus 10 factorial over 2 factorial times 8 factorial times 0.3 squared times 0.7 to the 8th. Okay, well, that's 1 minus, and we're going to plug this into a good calculator now. Obviously, 10 factorial over 0 factorial times 10 factorial is 1. Let's calculate that. Just gotta bring up the right calculator. Okay, so 0.7 to the 10th is 0.282475 249 plus, now we take this 10 factorial over 9 factorial, that's going to be 10 times, now we have 0.3 times 0.7 to the 9th, and that's 0.0121. $0.60821. Plus, and now 10 over 8 factorial is 10 times 9, 90, divided by 2 is 45, times, now we got 0.3 squared times 0.7 to the 8th which is 0.005 1883209. We will round this off when we're done, but now we're going to take this whole thing, plug it into the calculator, and figure out the final answer. And I'm just going to note that there should have been 0 in here. Oh, 005 1883209. Close my parentheses, hit enter. So the answer is 0.6172172136. And we're probably safe rounding that to 4 digits, 4 decimal places. 0.6172. That's it for this video. If you have any questions, please get in touch.